Alright, hello class. In this video we are moving on to the next module. So we are moving away from vector valued functions and we are going to start talking about planes and surfaces, and that's just the first sort of section of this module. This module is all about, well, it is basically about surfaces. This is about functions of several variables. Okay, so let's break it down in the way we've described already a few times, and then we'll start talking about how we visualize these things. So that's really just like with the vector valued functions. We're going to begin by talking about how we visualize all this stuff, and then we'll start talking about, well, how does calculus make sense in all of this. All right, now I always like to bring it back to what we've been talking about before, which is that with vector valued functions, we increase the number of dependent variables to 2 or 3 while still keeping the one independent variable. So our one independent variable was t in this case, while the 3 dependent variables were x, y, and z when used. And when we did this, it always made just a single curve in space. Okay, now there was a direction of travel, there's motion, velocity, speed, and all of that, but these vector valued functions, or vector functions, made curves in space. All right, and while there were vectors at each time t, what it was really doing was tracing out a curve across time. What this module is going to be looking at are, we'll just call them surfaces. Okay, but these are technically functions of several variables. Okay, so what exactly does that mean? Well, it means that what we're looking at is something like this. So if I shift over just for a minute, in our Cal 1 and Cal 2 world, and pre-cal and algebra, it was always stuff like y equals f of x. Okay, or it could have been y equals f of t, or it could have been x is some function of y. Okay, it was always something like this. So one independent variable, one dependent variable. Okay, what surfaces are, they're functions of several variables. So instead of a y equals f of x, we may have something like this: z equals f of x comma y. Okay, so this will give us a surface of some kind. Okay, another way to represent this would be something like this: capital F of x, y, z equals 0 or equals some constant. This will also give us a surface in 3 space. Okay, so these spit out 3D surfaces. Okay, so what we've done here is now we have, instead of increasing, and let me move this back, okay, instead of increasing the number of dependent variables this time, we've increased the number of independent variables. So we've gone from 2 to 3 independent variables, and are only considering one dependent variable. Okay, this one is sort of a more implicit thing, and we'll talk a little bit about what I mean by this. This is the more common one. Okay, but we could have also comma t we could do a function of w equals f of x, y, z. Let's say w equals g of x, y, z. Okay, there are many ways we can do this, but essentially what we've now done is our independent variables are now our spatial variables, usually x and y, and then we'll have one dependent variable, typically z. So this is usually what we're going to be looking at, is a function of 3 variables here. So the natural question is, well, why am I calling these surfaces? Well, it's because when we take a look at this stuff, we do get a surface. For example, if we say that z is equal to f of x, y, well, for each x, y we plug in, we get a unique z. All right, so each point x, y, and this is on the xy plane, gives us a height z. Okay, so what ends up happening is, for example, if this is one of my points, let's call this x1, y1, this is going to correspond with a point, let's call it z1. And then this point here will correspond with another z, and another z, and another z, and when we put it all together, what we end up with is a surface of heights, okay, making a surface. All right, so if this idea seems fairly complicated, don't feel bad. It kind of is. And this is really where I feel like I say this a lot, but this is where the trouble of Calculus 3 comes from. It's visualizing all of these things. So a lot of what we're going to start this module with is just giving us ways to describe or figure out or talk about what these objects look like. Okay, so and let's start with the most basic of these surfaces, which is the plane. And it's going to seem kind of familiar once we get to the formula, and we'll see why in just a second. But let's talk about the. All right, so planes. Planes are, I'm sure you remember talking about them in geometry. They're essentially just our flat surface. Okay, they're a flat surface. It's sort of like walking on the floor. The floor of your house is a plane. The ceiling's a plane. The walls are planes. But they, it doesn't mean they have to be horizontal or vertical exactly. Ramps are planes. Okay, so now that we have vectors, we're actually going to define planes using vectors. Okay, well, how do we do that? Well, here's how. Okay, we use a vector normal to the plane. Okay, well, what does that mean? Well, every plane will have a vector, and actually a bunch of vectors, that is perpendicular to the plane itself. So I always like to say set a pencil down on the table so that it points straight up. That would be a normal vector to the table. Or you can drop it, like set it on the floor and have it point straight up. That would be a vector normal to that plane. So essentially what we want is a plane N that is perpendicular, or I think I said that wrong. We want a vector N that is perpendicular to the plane. All right, more rigorously, more specifically, this actually means that N is perpendicular to every vector that lives on the plane. So any vector I choose on the plane will also be perpendicular to N. So in other words, this vector is perpendicular to every other vector, or just every vector on the plane. Okay, so a normal vector and a point is all we need to define a plane. So instead of trying to define it, you know, maybe by the points it crosses through, like we would need 3 points or whatever, we get the equation of the plane. Okay, we get the equation of the plane with a normal vector N and just any point on the plane, x naught, y naught, z naught. Okay, well, how do we do this? It basically comes from just what we've said here. If we have a vector that we know is normal and we have a point that we know sits on the plane, we've got everything we need. So if N, which let's say is the vector ABC, is normal to the plane or is perpendicular to plane P, and x naught, y naught, z naught is a point on the plane. Right, exactly how we drew up here. X naught, y naught, z naught's on the plane. N is a vector that is perpendicular to the plane. All right, now I'm going to choose any vector that sits on the plane. Let's let V be the vector that sits on the plane. So suppose let's suppose V is a vector that starts at x naught, y naught, z naught, and terminates at the point, let's say x, y, z, and I'm just going to say it's any vector. So I'm just going to pick any vector that terminates at any point x, y, z on the plane. So notice I'm not assuming that V is in standard position. I'm not assuming it's actually starting at the origin. It's starting at this point and going to this point. So that means that V is actually defined like this. So V is actually x minus x naught, y minus y naught, and z minus z naught. Okay, if you don't see that immediately, just take a moment to give it a think. All right, about what we've discussed previously about vectors. Okay, and by definition, dot v must be 0. Well, why is that? Since n is perpendicular to v. So this tells us that n, which is the vector ABC, dotted with this vector x minus x naught, y minus y naught, z minus z naught, that dot product needs to be 0, right? Since these two vectors are perpendicular. So when we take this dot product, we'll get a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0, and this is the equation of the plane. Okay, it's a times x minus x naught, b times y minus y naught, and c times z minus z naught. Well, this may look familiar if you think about lines. Remember the point slope form of a line, which is y equals, or y minus y naught is equal to m times x minus x naught? Okay, well, if we instead made our m something like this, negative a over b, which I'm just doing that for, just demonstration purposes. I could write this as, delta x over delta y or whatever. Then if I multiply the b over, I would get b times y minus y naught is equal to negative a times x minus x naught. And if I were to move this over, we'd get a times x minus x naught plus b times y minus y naught is equal to 0. So this was the equation of a line. So that's our linear expression in 2 dimensions. This is what we got as the definition of plane. And this is our linear expression right, in 3 dimensions. Right, the variables themselves are linear, and we get an a times the x stuff, a b times the y stuff, and a c times the z stuff. This is sometimes changed to this, ax plus by plus cz is equal to d, where d is equal to ax naught plus by naught plus cz naught. So all you do to get from here to here is distribute the a, the b, the c, and move the naught terms over to the other side. Okay? So let's take a look at an example, and I'll show you like what's going on here, why it works the way it does. All right, so for this example, let's find the equation of the plane that passes through the point 3, negative 4, 5, with a normal vector n equal to negative 1, 2, 3. Okay, now, hopefully here you're starting to see why I made such a big deal about how we notate points versus how we notate vectors. Points we use parentheses, vectors we use sharp parentheses. Okay, that makes this the normal vector and this the point. Now, this might seem fussy, but I'm going to go through and label this as x naught, y naught, and z naught. Okay, so that I know where to put it in my formula. This is the point, so it's the naught stuff. As here, this is the vector, so this is A, B, and C. Okay, so the equation of a plane is always the x times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And now you just fill in the pieces. Right? It will be negative 1 times x minus x naught, which is, in this case, 3. All right, then it'll be plus b, which is 2, times y minus y naught, so that will be a negative 4. I'm writing this way more explicitly and redundantly than I probably should, just to get the point across that just like when you're finding the equation of the line, okay, with finding the equation of the plane, you leave the x things, the y things, and the z things alone. The letters and then the x naughts or what have you, those go away. Okay, then it will be c, which in this case is 3, times z minus z naught, which in this case is 5, is equal to 0. Okay, so we get the equation negative x minus 3 plus 2 times y plus 4 plus 3 times z minus 5. Okay, now I am actually going to simplify this down a bit. I'm going to distribute that negative, so I get negative x plus 3 plus 2y plus 8 plus 3z minus 15 equals 0. Right, combining like terms, I should get negative x plus 2y plus 3z. I'm going to put it here at the end. The 3 plus 8 is 13 minus, not 13, sorry, 11 minus 15. That should be, what, negative 4? Is equal to 0, and so this will be negative x plus 2y plus 3z is equal to 4. Okay, so I will say though this suffices. However, this might be a little more manageable to deal with, and especially when a natural question is, well, okay, great. I told you that this is the equation of the plane. We got it in a logical manner that maybe made sense, maybe it didn't. How are we certain that this is actually a plane? So let's take a look at it. Okay, so I'm going to start graphing it. Now, we haven't talked about graphing surfaces in 3 dimensions yet, but before I do that, I'm just going to start looking at what's happening on the different axes. So let's say I look at just what's happening on the xy plane. So the xy plane is when z is equal to 0. Okay, so when z is equal to 0, this disappears, and we end up with negative x plus 2y equals 4. Okay, so we can move the x over, divide by 2, and we'll get y is equal to 1/2 x plus 2. This is a line. It has a slope of 1/2 and a y-intercept of 2. So we have a y-intercept of 2, and then rise over run, so as it goes out 2, it goes up 1. Okay, so looks something like this. Alright, so that's what's happening on the xy plane. Alright, so now we're going to look at the xz plane. Okay, so now we're just going to treat z like it's the y-axis for this plane and let y equal 0. and we'll use purple for this one. So when y disappears, we'll have negative x plus 3z is equal to 4. So we'll have 3z is equal to x plus 4, so z is equal to 1/3 x plus 4. All right, so we get, 4/3. So we can imagine, say 4/3 is about right there, and we have a positive slope, so it's going to look something like this. I'm not going for exactness here. I'll go to some graphing software for that when I'm ready. And finally, you guessed it, we're going to look at the YZ plane. And this is where we let x equal 0 and pretend, maybe not pretend, but treat z like the vertical independent axis and y as the independent axis. All right, and we'll do this one in green, let's say. So letting x equal 0, we'll get 2y plus 3z is equal to 4. So 3z is equal to negative 2y plus 4. So z is equal to negative 2/3 y plus 4/3. Okay, so we now have a slope. Notice that it's the same z point, right? But now we have a negative slope. And like I said, I'm not going for exactness here, clearly, because I messed that up completely. But the thing to note here is that what we've done when we've isolated this down to just the axes, the basic 3 double axes options, we got lines every time. Okay, so I can almost start to maybe have a wonder at what this might look like in 3 dimensions. Okay, so on the xy plane, I'm going to just do the triangle here, but that line, we're in the negative x but the positive y, so that looks like it'd be here on the xy plane. Okay, and we could continue it on if we want. But then on the xz plane, we have a line, it's in the negative x but the positive z, so the purple one will probably look like this, and I just connect them. Okay, and then in green, we have on the yz plane this line, and the way it's actually drawn here, I can just actually copy here. Okay, now these 3 guys together, this triangle gives a representation of this plane. What we've done here is if we were to look at it from one of the sides, we'd see this. This is one of the sides, but we can imagine that the z-axis is coming out this way or this way. Okay, so we're almost looking at shadows of the plane. Okay, so let's actually graph these lines on a 3-dimensional graph, like actual software, and see what we get. Okay, so here's our graphing software. Now, here is in red the x-axis, in green the y-axis, in blue the z-axis. And so here's our first line. That's on the xy plane, and as you can see, that just sits right on the xy plane. And what that was modeling for us is if we looked at it dead on, right, from above down to it. Okay, so there we go. Then there's our second line in purple, right? That was the xz plane. Whoops, let's flip it around so it matches. Okay, the XZ plane. All right, and then finally the YZ plane in green. And we see the three of them together. This gives a representation of the plane itself because I can spin it around and it's basically describing the plane, helping us visualize it. Notice I haven't graphed the vector, like that normal vector or the point itself. We can totally do that. In fact, I will do that next, but I also want to show the plane itself. Okay, and I will come back with some of those. All right, so here is the plane. So as I was trying to say, these lines sort of give us a representation of where it lives. But if we were to fill all that in, we would get this plane here. Okay? So at the different axes, what we're seeing is where the plane intersects the XY plane, the XZ plane, YZ plane. Okay, so if we knock these off, right, here's the plane itself, here's the point we started with, and the normal vector we were given. Okay, so notice I have the vector not in standard form, but here coming off of this point. But notice, or remember, vectors are equal wherever their starting point is. So I could have moved it here. Right, this is also in. And notice also that we could have used really any vector that was perpendicular to the plane. So it turns out that, you know, there are lots of vectors on the plane that are perpendicular, and you can use any of them to get the formula for the plane. So the equation itself is not unique. Okay, so this equation we got here is not unique. We could have used a different, or we could have been given a different vector that was perpendicular to the plane. However, what ends up happening, and you'll see this a lot, so let's clear this up and take a look. All right, so, you know, depending on how this was done, you may have, and say you did your work and you got down to here, but when you checked your answer in the back of the book, it showed this. And you might think, oh no, I'm completely wrong. However, all we've done is multiplied everything by -1. So this would be using the negative of our normal vector, which, as we can see here, -n will also work just fine. Okay? Or maybe you did all your work and then you found that you got something like this. You got -2x plus 4y plus 6z is equal to 8. And you might also think, oh no, I did something wrong. But actually, this is the exact same plane. All we've done is multiplied everything by 2. In fact, we're using 2n. Okay, 2n is still going to be perpendicular to the plane. So be on the lookout for this, because this can come up. I mean, you might even find that your plane looks like this: negative x over 3 plus 2/3 y plus z is equal to 4/3. Right? This might be the plane you got when, in fact, this is the answer that the back of the book lists. still the same. This is just using 1/3 n instead of the n we were given. Now this does, this comes up more in situations where you aren't given the n, because if you're given the n, you're just going to use it. This comes up in situations where you maybe have to find n yourself. All right, so for example, say we want to find the equation of the plane crossing through these points, 2, 0, 0, 0, 2, 0, and 0, 0, negative 6. All right, so we can actually plot that fairly quickly. Just the points themselves. All right, so for x, that's 2, 0, 0. For y, it's 0, 2, 0. And on the x-axis, it's 0, 0, negative 6. Okay? And I did this sort of on purpose just to show that this is actually a quick way to graph a plane if you know where it crosses each axis, like what point it intersects the x-axis, the y-axis, and the z-axis. Okay, you can actually get a nice look at what, well, the plane looks like. Okay. All right, so now if you have graphing software, all right, with graphing software you can kind of see, let me zoom in a little bit. We see the plane intersects at 2, 2, and down here at negative 6. So this, I do like using the little triangle because I feel like it gives sort of the nice representation of what's going on. Okay, and so here I threw in the triangle so it's a little easier to view. Okay, so again, like I said, I just like to use this to give me a nice visual. Okay, but it doesn't give us the equation if we need to work with the equation for whatever reason. Okay, so in order to find the equation, what we need, well, we have a point, right? So we need a vector and point. So we have plenty of points. We have 3 points we could use here. What we really need is that normal vector. Okay? So in order to find it, I need some vectors on this plane. And, there are countless vectors. There's an infinite number of vectors that live on this plane. So I just need to make some. Okay? And since I have some points here, I'm going to make this vector, say the vector that goes from 2, 0, 0 to 0, 2, 0. So let's call that V. And we can make our next vector, let's make it the vector that goes from 2, 0, 0 to 0, 0, negative 6 here. All right, let's call that W. So V is going to be the vector, well, it's going from 2, 0, 0 to 0, 2, 0. So it's always the terminating point minus the starting point. Okay, so V is going to be negative 2, 2, 0. All right, W, well, that's going to be 0 minus 2, 0 minus 0, negative 6 minus 0. So W is negative 2, 0, and negative 6. All right, so we have 2 vectors on the plane. The reason we need that, because if we want to find n, right, the vector that is perpendicular to both V and W, that is going to be, or it could be, say, in this direction, that's going to be their cross product. Now, which one we get depends on what order we set here, but again, we just need a vector, right, that is perpendicular to both of these vectors, therefore perpendicular to the plane. So we will calculate the cross product. Okay, so we will put in our v, which is -2, 2, 0, our w, which is -2, 0, -6, and copy down our first two columns. Oops, don't need that last line. And then start calculating our cross product. Right, so we'll ignore that first column, and it will be -12 minus 0. Okay. Then we'll ignore that column, and then it will be plus j times 0 in the main diagonal, and then minus a -2 times a -6, which will be a positive 12. Okay. Then plus k, now it will be 0 in the main diagonal again, minus a -4. All right, so we get -12i minus 12j plus 4k. So I got this vector, -12, -12, 4. Now, this will be a vector normal to the plane, okay? However, it's kind of unwieldy. In fact, I'm going to call this n star. So I'm going to set n, or I'm going to choose n to actually equal, I'm going to simplify this a bit. I'm going to multiply by -1/4. And you might wonder why in the world I would do that. Well, that's because that's going to change this to be 3, 3, -1, which will be a much nicer vector to work with than this one. All right, so if we go back to our graph real quick, here is v cross w. First of all, it's fairly long, but it can be kind of tough to see that it actually is perpendicular to the plane. In certain angles, it doesn't really look it, but so that is, yeah, in that angle, it kind of does. So here's, you know, the v cross w. Here's the n I decided to choose, and notice it's still perpendicular to the plane. It's just going to be easier to work with. Okay, and at the end of the day, if you chose, say, to go from this point, then your w was, say, this vector. Let's say you chose this vector instead, right? You would get a different n out, or a different n star. It would still be parallel to the one that we found. All right, so don't freak out if your numbers don't match exactly what the answer in the back of the book says. And also, feel free to choose a nicer vector when you get down to this point if you see that you can divide by whatever. Okay, now, here we can use whatever point we want. I am going to use this point here. But at the end of the day, it really doesn't matter. So, we've got everything we need. We have a point, 0, 0, -6. It's just like with lines. It doesn't really matter what point you use as long as it's on the line. And we have our normal vector, right? So that's going to make this x naught, y naught, z naught. And that's going to make this A, B, and C, right? So remember, it's A times x minus x naught plus B times y minus y naught plus C times z minus z naught. and maybe and equals 0, and maybe when I fill this out you'll see why I used this point. It will be 3 times x minus 0 plus 3 times y minus 0 plus 1 times, minus 1 times z minus a negative 6, so plus 6 equals 0. Right, so we get 3x plus 3y minus z minus 6 equals 0. All right, now this is the equation of our plane. You may see it written like this instead. Okay, or now this, if I just move the z over, you would get z is equal to 3x plus 3y minus 6. Here is a z equals f of xy. Okay, so this is the function version of this surface, whereas here, this is the version that's capital F of x, y, z equals 0. Okay, so just showing this to show that a lot of times they can both be set up in the same way, because if you just move the z over and call this capital F of x, y, z, you get it into this form. So this is just a more general form of what we're dealing with here. Of course, sometimes you may have a situation where you can't do this, right? You might actually have a y equals something like g of xz, or an x equals an h of yz. Okay, usually we're looking at it in terms of the z equals f of xy, and then sometimes it just can't be made like this at all. So if you had x squared plus y squared plus z squared minus 9 is equal to 0. Solving for any of these is not actually going to give you a nice function, so we just leave it in this format. Okay? All right, so that is planes. I'm going to end it here, because I think that's a lot for one video. But what I will say is what we did in the previous example, right? This previous example where I went to each particular xy plane and looked to see what was going on there and then moved it to 3 space. Okay, this is how we're going to tackle visualizing every surface. Okay, these are called traces. This is the xy trace. This one in purple was the xz trace. And this one in green was the yz trace. All right, and this technique of looking at these various traces and putting them together to get an idea of what the entire surface is doing is what we will be doing to start with when we first start visualizing more complicated surfaces. All right, so that's a bit of a sneak peek at what we'll be looking at in the next video, and I will talk to you all then.